Hi guys, and welcome to a machine learning tutorial on how to design a cat versus dog classification system using Keras and TensorFlow. So here I'm just showing you some of the images that you'll get in this classifier. In this example, I'm just showing you from the test folder, which has around 12,000 images, while the train folder has about 25,000 images. So because I'm actually using Ubuntu, it does take a while to load the images. So as you can tell, I've actually opened this folder and it's still buffering, as you can tell with the spinning icon here. But this is just a pure representation of how the images will look. And I'll be showing you how the images look actually using Jupyter Notebook, which will be much quicker to use. So here I'm just opening one of the few Jupyter notebooks that I have for this project. So we'll be working with the edges, colored, and the grayscale. And so here, starting with the edges, and the main reason for working with this is this one will allow me to show how you can train a machine learning algorithm only using the edges. So to show you how the edges will look, let me just open a new tab here, a new terminal. And so I've ls into the folder, and as you can tell here, data. So I'm basically using a virtual environment, and I have this file here called plot image borders, and I'm using cv2. So as you can tell here, I'm going to import cv2, import numpy, and from the images I have a list where I have images of I'd be likely using. So I've just listed one for this example case scenario, and it's an image from the test folder with the ID number of 1818, and it's an image of a car. But just so you see what I'm going to do, I'm just saying image, the first position, which is just this string for the path of the image, and I'm reading this image using cv2. And when I get that, I get the edges of the images using cv2.canny, which basically takes the image and returns it back as only the borders. So that will return me the edges. And so that you can see each one of these, I'm going to copy this and paste, and I'm actually going to list here the images. This one will come back as image, and let me just do one more. So here we'll have small icon, and it will be image data, and edges here will actually be edges. So to recap here, what I've done is, as you can tell here, we have edges, which is just cv2.canny, take the image 250 by 250. So what this actually does, it takes the image and looks for the lines, basically the outline. So if in case you're actually drawing a cat, imagine you are drawing the cat, and what you'd have actually just do is draw the outline, then fill in the colors and so on. So it basically looks for colors by usually a change in gradient of the colors, and that's how it identifies the borders. And here there is now image data, which is just this image from the edges, and then it's been resized to 64 by 64 pixels. And that makes it just smaller, because when you're training the image classification system, you want an image that is as small as possible. That's basically what's going to be used by cv2 here to display a small icon. And then you have image, which is now the main image, which basically has not been scaled. So let me now save this. Back in the terminal, I'm just going to do Python, then plot image border.py. So now we have our three images here. So as you can tell here, this here is the main image, the original unedited. And now we get this one, which is edges, which is just looking for the outlines of the images. And this final here is just a small icon, which is basically what will be sent into the classifier, which is the edges shrunk down to a smaller dimension to work with the model. And the key thing here to note is this is important because usually when you're training your model, you never usually give it an image of an arbitrary width and height. You usually scale them all to the same height. So if it's usually a smaller image, which rarely do you scale up, but usually scale down. So in this case, as you can tell, we have a larger image and then the smaller image which you're going to be training with. And just for pointers here, you may be thinking that that's too small of an image, but there is this first training example which you usually do when you're doing data science and image classification, which is called the MNIST dataset. And the MNIST dataset is usually about classifying digits, which is all the digits, which is usually from 0 to 9. And what you get back is digits which usually look something like this. And you actually have to classify which digits you see. And the MNIST images dimensions are usually 28 by 28 pixels. And here I'm working with 64 by 64. So it's much bigger, just to prove a concept that you can have a small image and the image will still be able to classify. Even though the more important thing here to note is, usually since when you're doing classifications for images, people usually go with GrayScale or the image in full color, which is just RGB. So if you decide to go with the edges method or GrayScale and so on, 64 by 64 pixels is still plenty large, and even the most largest you can go is for around 128. You can go higher, but you don't necessarily have to. And the main point here is I want to point out that when I was starting this, I wanted to start with about 200 by 200 pixels, which I thought was about fair enough for the model that I was training, which is here. So this is the code of the model that will be actually doing the classification. But the main point I want to say is, as you can tell, I went 64 by 64. So I started with about 200 by 200. It was actually not getting any high amount of accuracy. And I could tell because what it's doing here with the cat versus dog classification is it needs to classify whether an image is a cat or a dog. And the only way to actually tell is basically it needs to find patterns within the image. And one thing here that usually is used when you're doing this is what's called a sliding window, which is a small window which the image uses to analyze. So just to go briefly on what's actually going to be how the model works, this is a 3 by 3 window. So it means in your image, in the example, let's say we had a 200 by 200 image and you had a sliding window that's about 3 pixels small. So you have an image that can basically span 66 small windows horizontally and vertically. So it's a very small window that slides looking for a pattern. So imagine if you basically got your image and then you segmented it into 64 actually it will be 66 by 66 because it's width and height. So in this scenario you'd have your 200 image, 200 by 200 image, segmented into about 4,356 small cubicles, and basically you'll just be checking within each one of those cubicles whether there is something that can tell you as a telltale sign that this is a cat or a dog. So the main problem here would be the bigger the image and the smaller the window, the lesser the chance that you'd have a unique feature noticed inside the window. So to put it into an example, let's say you have this example of a cat that you're working with, and let's say we take this one of a dog. In order to actually get a unique feature, you'd have a very small window. Wish I could draw this one just to see, but just imagine you have this small little box and you need to tell from that small box whether that is a cat or a dog. The most key things you'll be able to notice is maybe the shape of an ear or a nose or something, but the more data is in your image, the harder it is for your classifier algorithm to figure it out, because there will be varying angles of the dogs, whether the nose is pointing towards the picture or away from the picture. Maybe there's a picture where the dog's nose is a different shade compared to another one. So there's a lot of complexity that goes into this. So that's why you need as the data to be in the most the most easiest easiest way for the machine learning algorithm to figure it out. Now the main point here you actually want to point out is, now because in this example we are dealing with cat versus dog, if I actually showed you an example of a dog and you don't know what a dog is and you're just supposed to give me your educated guess whether this is a dog or not, your chance of actually getting it right will be about 50%. So if I show you another picture of another animal and I asked you, is this a dog, and you still don't know what a dog is, maybe you'll still be getting the same amount of accuracy. Just the same way, let's say I showed you a picture of a celebrity which you've never heard of, and I asked you, is this that celebrity? You say, I don't know. So you'd have to guess correctly, say yes or no. So even if you say yes or no, and you still haven't gotten a clue whether that is the right answer, you're not actually going to be getting better at predicting. But at the moment where I tell you this is him, the next time you see another different image, you'll say, yeah, that's not him. And that's the key main point that actually goes into machine learning and how to predict this code. So let me just, if you're actually interested in learning this, I recommend looking up Jeff Hitton. He's a lecturer at Washington University. His courses actually has a hands-on approach on how to use Keras and how you can actually build machine learning scripts from scratch. And I actually liked it because you can actually know how to build things from a practical angle, and he actually shows a realistic approach of how to do this, because instead of starting from the angle where you need a powerful machine to design machine learning algorithm, which you may think maybe you need a fast CPU with an NVIDIA GTX with the highest specs, basically, so you can make a really nice CNN, which is convolution neural network, that can take images at full clarity, maybe even about 1080p, and then give you an answer. The key thing here is it shows you how you can do this with basically your average laptop MPC, and that can actually scale upwards. And to put this, for example, as an example into how this would work, the picture that I showed you of an MNIST example, that's a small image and it got enough accuracy for it to actually be used in practical life. And people who actually do create deep neural networks have actually found that creating smaller ones are not getting enough accuracy, and increasing the deepness, well, the layers they have inside their neural network is getting them more accuracy. So it's not from an angle of big and then moving downward if necessary. It's usually from an angle of starting with a minimum small set, then understanding the parameters you need to change to make it bigger and deeper to get more and more high accuracy. So the key point here is, when you are designing this, think from the angle of, you know what you're doing, you need to make a small neural network, because the thing is, when you are not running this, usually there is an epoch, which is usually the first iteration of through the entire data that you're using, trying to look at the pattern inside the data. So that's the first epoch. You went through the whole data set, had an amount of accuracy, then it goes through it another time and another time and another time, and so on until you get a high enough accuracy, avoiding another thing called overfitting, which is just memorizing the data and not generalizing. That's why usually you split the data into validation set and training set. And yeah, that's the key logic of how to design this. So enough talk, let's actually now get to it. I've shown you how the image looks, so I'll show you how to actually design this using the edges. So now you have CV2, import random, numpy, tqdm, which, as I said, is just for looping, pickle to save the data, because we'll be saving this data that we'll preload, which may be useful because you'll know it usually takes around 5 to 6 minutes to run through the whole data and save it as a numpy array. So maybe the next time you want to do this, you may decide to use a pickle or just reload it, whichever works for you. And from Keras, you import sequential, which is how you define your model at the start. Then convolution 2D, which is just images are in 2D, not 3D. So convolution 2D, basically taking your image in 2 dimensions and then analyzing it. So you have max pooling, which is just pooling, which is basically like reducing the dimensions, because they usually get really large when you have filters, which is basically I'll show you later on when you get there. And activation, which is an activation function, dropout, flatten, and dense. And then activation is just an activation function. Dropout is for dropout. Dropout means that basically you have cells which are usually called units. You can imagine, okay, think of them as cells, which are just where the data falls through from layer between layers. So each layer has its own units. And dropper basically says what percentage needs to be randomly deactivated through every epoch, and the reason for that is to avoid overfitting. So it's a method that's been proven to actually help for avoid overfitting. Another one is flatten, which is just once the data has been fully analyzed by the filters, flatten it so that a dense layer, which is this one, can look for patterns within it. So get your image, flatten it, then to predict it. So it moves from a 2D to a flat layer. That's what's happening here. And then TensorBoard, that's useful. And now you want to, when you're running through this, you may actually want to compare where one model is better than another. And instead of comparing maybe even the last digit, which is the percentage of accuracy you get at the end, it gets this information, stores them in a CSV, I believe, or JSON format. Then you can it plots it for you. So it's like a web page. So actually just get some data that's been stored in a folder and then plot it so you can actually see the graph of how it does in terms of accuracy, loss, and validation accuracy and validation loss. And early stopping now is useful for whenever the validation loss starts going upwards for a duration where you've specified. Let's say you say if the validation loss does not decrease after 5 iterations, which is usually what I do, stop learning, quit. So that's what's going to happen. And a model checkpoint just saves the model which had the lowest loss, validation loss. So that way, even you could say an early stopping of 10, 15, still it will just check for the model loss that has the lowest validation. And okay, so using that, that's every import that you need to do. So finally here is matplotlib for plotting. Plot inline, so just means inside these Jupyter cells actually plot whatever you want inside the Jupyter plot instead of it popping out. So here what I'm actually doing is os.list data. So I'm listing what's inside this data folder, which is the folder directly here, and you have test and train. So you can see train, test, and sample submission, which is just for Kaggle. I'm actually going to return the data. That's not important right now. So what we actually have here is test and train. And the training is what actually we're going to be using for training. The test is actually just what I'm supposed to actually use to supply the sample submission once I actually have a model that I'm going to be using. At this point, I'm actually not working on the submission because I'm still tinkering with the models, but I actually wanted to show you how the edges classification, how to use colored and grayscale, basically how to design a model that classify images through and through. So here you can tell that using os.lister, the train folder has 25,000 images, and the test folder has 12,500 images. So that covers the two. And just to list, as you can tell, you have just taken train images and listed them. This is just all the files inside this folder. So now I have all the file names inside this folder, and the train images, that's taking the first 10 images from this list. I can tell it's cut.something, cut.something, .something. So that's how I know whether an image belongs to a cut or not. That's how they decided to arrange this data. That's just an FYI, just in case you're interested. Sometimes you'll find them put inside different folders. So one folder for a dog, another one for a cat. So it all depends on how you get it, but how I'm actually going to show you how to do this won't matter whether it's in one folder or another. You'll still be able to move through the whole process without any type of issue. So now you can tell from the test image, these are not annotated files, they're just file names. And that's how you do it. Now you have your data. Now what I'm doing here is I'm taking test images data, and I'm setting it to an open, well, a blank list, and so I'm actually then going to loop through it. And let me just start running all of this. So here I'm just looping through them with TQDM, which is actually going to show me this, which is a progress bar of how far it's going, which is useful just in case I want to know how long the for loop will take, or if there's any issues, because usually this takes around, it can take up to 4 or 5 minutes, and you may be wondering, is it 10% through, 15% through? Yeah, you can actually wonder how long it may take, but this gives you an idea of how long it takes, which can basically help you be more patient when you're waiting for it to finish. So here I've just taken the name of the file, and then I've appended data/tests so that inside this test image I can load it using CV2. Then I convert it into GrayScale using this line, and now that the image is in GrayScale, I can take the image and I resize it into 64 by 64 pixels. And finally, I use CV2 Canny to get the borders, as I showed you previously with the cat image. So while I run this, it takes around 1 minute to finish. I'll wait for that to finish, and so once that's done, what I'm actually going to do is turn that list into a NumPy array. And this is important because when you're running your machine learning script, it usually expects the list to be in a NumPy array format, so you can't actually just feed it a normal list. So next step is doing this for the train images. The only key difference is here I actually know the label, so I have my empty list of data, my empty list of labels, and I do a shuffle because here, as you can tell, there is cat and dog. There is a risk that actually you'll be getting cats at the beginning, then dogs at the end. Not so much, because as you can tell, it's kind of a bit random, but this is good practice to shuffle so that actually they don't come in the same format. So what I'm doing, just once I have my data in a shuffled format, I can just load the image in the same way, turn it into a GrayScale image, resize it into a 64 by 64 image. Then I get my border image, and then using that I append it first the way it is. Then this one flips it, mirrors the image, which is basically flipping it. I believe it's vertically, so it's flipping an image like a mirror, the way you can look at your mirror where your left is right when you are facing the mirror. So that's basically what it does. The advantage of doing this is a mirrored image is not exactly the same as the image as it looks before it's been mirrored, and that gives your training script more data to work with. So in this case, just because I mirrored this image, I could have done a lot more, and things maybe flipped it upside down, which is not really useful because rarely would you get images that you're training with which are being flipped upside down. But in case you imagine that's a scenario, you could have done that also, and now you get more and more training data to work with. So with that, now I have twice as much data that I had before, from 25,000 to 50,000 images, just to, because now the other 25,000 are the flipped images. And for the labels, I'm doing the same thing. What I'm doing is just checking if the image starts with cat, I append a 0 to the labels twice because there is a flip effect. Otherwise, append a 1 and a 1. And the reason for that is just 0 is a cat, 1 is a dog. That's the main thing. And while this takes a while to finish, this is going to take a little bit longer, 6 more minutes. So this is the main reason that I decided to use TQDM, because it actually gives me a inkling of how long this may actually take. And just to show you one more important thing is, here's stats from my PC. As you can tell here, I have around 14 GB total in RAM, and it has around 4 cores. And the cores are actually a little bit busy but not too maxed out because of this process of well, analyzing the images and saving them into an NumPy array. And because this is the edges dataset, it actually doesn't take up too much RAM. In fact, because I'm actually saving the images as a 64 by 64 pixel image, and all of this data usually is saved into RAM when you are training your model. So with this in consideration, the smaller fingerprint you have in terms of RAM, the better you have, and the quicker your model runs. So it's a win-win scenario. Start small, move big. Instead of starting big, having more problems of looking whether your RAM is enough and all those other kind of issues, just start with small, but not too small that it affects performance. So you could even start with about the same 28 by 28. It would even train much quicker, and you'd have enough time to basically see how quickly it trained. So then you can move to maybe 50, 60, and so on. So in my case, I was satisfied with 64 because I was getting on average over 80%. I'm actually now looking to go into 90%, and not in particular by changing the size of the image, but doing a little bit of scaling on the model. So this may take me a while, and I more likely will make a follow-up video on this. But for now, just know this is how the model will be training and how it will be looking at. So here I'm just turning the train images and labels into a NumPy array, and then doing a reshape, which you really have to do for reasons that it's just a custom, so that you can fit it into your model. So you have your 64 by 64 pixel, and 1 is basically the color depth. So RGB, that will be 3, grayscale, that will be 1. So the reason RGB is 3 is because you have red, green, and blue. Grayscale is just one color, 0 to 255, which basically is 0 being black, 255 being white. That's it. And this -1 basically just explains, I think reshapes it to a way that the model expects it to be. Well, the data now comes as, well, stacks of single lines. Basically, the data is now reshaped so that it comes in a format where it's the number of images that you have, in this case 50,000 by 64 by 64 by 1. That's how I believe it's actually going to be, but you really won't go too wrong with just this. And the only thing you'll probably be changing here is the width and the height, and you could actually just change this into a variable up there. When you're just changing the dimensions every, like here and here, it just affects everyone here, and you should be good to go. In my case, I want to have a real hands-on experience so that I can actually know at the back of my hand what's going on. So that's why I'm avoiding code that feels a little bit more like copy pasting code from somewhere without a full understanding of how it works. So the next step here is make sure that runs, waiting for the other one to finish. This one just basically all the pico files will just be saving the data as picos, and they are pretty large. Let me just show you how large they can get. That will be model data, and now you're looking at the edges. So here's the edges test images. It's about 253 megabytes. The train images is about 614 megabytes, and the labels is usually the smallest, about 400 kilobytes. So that's 600 MBs, and it can actually usually gets much larger for different training data that you're using. So it's 614. There was one that actually went, I believe, almost to a GB. Yeah, the one time that it was going up to 2 GB almost was when I was working 200 by 200 pixels. So now it's actually shrunk a considerable amount. It's now 600 MBs, but it's significantly enough that I will not actually put it into my GitHub code, because all of those data, including all the images, will just make this, I believe, almost up to 5 GB worth of repo. And I have pointed out where you can get the data on Kaggle, so you should actually just be able to download the data for the images and train the model without any hassle. So here the next thing I'm doing is I'm defining the model name, which is how it's going to be saved. This is important for one reason, because this one is actually how the checkpoint model name will be saved here, and it's the model that usually is saved. And you can actually just use this one as you preload the model, getting any issues with that. So that's how you preload your model. As you can tell, it's using model or checkpoint. So if you once your model is saved and realize that this has the lowest validation point, that's how it's saved. And basically that's the reason why you need this model name. And when you how I usually name mine is using unique identifiers of how the model is. So in this case, the data comes in edges only, and the epochs are 100, how much I'm training it using epochs. And the convolution network at the top is 3x3, and I'm using dropout, which is this. So let's say if you actually don't want to use dropout, you can uncomment that, then remove /dropout at the end, and basically that's how you train a model. So while this one still runs, I'm actually now going to rename this into demo, for reasons being I've actually used this before and I've run it previously. So if I actually run this part of the code, the graph that I was telling you would actually be overwritten. And just to show you how that graph looks, this is TensorBoard log directory, which is logs, and that actually goes the same into this folder with this line of code that says TensorBoard will actually store its data inside the log folder, and that's the same folder I'm loading here. And thanks to that, and I can actually view how my models were training. And if I actually use the same file name, it'll actually overwrite that. And if I was actually going to let it run till the end, that will not be a problem. But this is just to show you how it works. So I'm actually not going to let it run till it finishes. So for that reason, I'm just going to rename it to demo and leave it at that. Okay, so while that, I wanted actually just to show you how the CPU clocks while it's in rest mode. So yeah, that's around, let's say around 20% per CPU core roughly. So that goes up higher when it's starting to train the model, just to keep it in mind, because that's the next thing we'll be doing. So I believe the next thing here that I need to do is run this and then train the model. So it usually takes a couple of seconds to start. If you don't get an error within the first 5 to 10 seconds, you know it's good. It's just preloading what's called a graph, basically how the data will be processed in the background. Then depending on your CPU, in less than a minute you should get this. Now here it's telling me the most important part. It's starting the first training, and the train has 40,000 images and validation of 10,000 images. This is based on this. As you can tell, I just fed it train images and train labels, told it to run for 100 epochs. The validation split is 0.2, which is basically saying take 20% and use that as a validation set, and 20% of 50,000 is 10,000. So that's how I get my validation set. And you may feel like it's a lot, but 40,000 is still pretty much enough for training, so I'm okay with that. Plus I actually want the validation set to actually be also have enough data to actually be critical on its own also. So the other key thing is model checkpoint, which basically saves the model as a checkpoint, and it saves only the best model. As I can tell you, save best only equals to true. It monitors validation loss, and this one will just basically be checking for anytime the model check validation loss has gone lower. If it's gone lower than any recorded previous time, it saves a new model with the same file name. And validation loss is also used here for early stopping, and it checks for patience of 5. So if 5 epochs have gone and the validation has not gone down, then there's an issue. And basically, not an issue, it means that it actually has met this criteria, so it actually just stops. And then you can just use your best model, and that will be it. So while this runs, I want you to pay attention to this, which is the accuracy, and it usually comes in a dot notation, decimal notation, 1 being 100. So now 0.52 means it has about 52% accuracy, and this is good for one key reason. When you are randomly guessing something, your chances of getting something right is about 50-50, but you will get some of them wrong, and that's how I would start going below 50%. Now you get to maybe 49, 48, and so on. And so if you see your model in terms of this scenario, you're only classifying only 2 things and you're getting lower than 50%, and it's not moving up in a consistent manner. It may move down and down a bit, but consistently it should be moving up. Just give it about enough time to actually start learning. But if it's actually just staying on the same ratio of randomly guessing, then you know your model actually not fitting, and basically you need to find out why it's not fitting. And as you can tell here, the epochs that I'm running is about 100, and each epoch has around 15 so minutes to run. This one has about 9 minutes remaining. And you have your loss, which is usually called log loss, and for now you really don't need to care too much about it. If you watch Jeff Hitton's video, he'll actually go into in depth about what it's about, just enough for you to figure out what log loss is. But just to put it into perspective, log loss is a way of checking the error in terms of a high specificity. So let's say a 50% accuracy will give you about a log loss of about 1 point something. So yes, and the lower your accuracy, the higher the log loss. You'd prefer your log loss to be below below 0, like 0 point something. And if it has 0.0 something, that's actually pretty good. You're probably looking at about 70 to 80% level of accuracy, and the higher you get to 90%, you're probably getting 0.0 something. So right now, if you can tell you the log loss of about 2 is too high, and as you can tell, the log loss is moving down quicker than the percentage is moving up higher. So that's the key thing to notice about log loss. So I'm actually just going to cancel this, just show you how the CPU was clocking. So all the cores were clocking at around 100%. So this actually goes high on the CPU cores. I'm actually not using GPU, I'm just using the normal CPU that the comp came with, my laptop in this case. If you had GPU, probably getting a much higher speed. So that's something also to keep in mind. The only difference is if you're actually using GPU, there's a little bit of making sure your code is using GPU. And I think the main difference is, instead of installing TensorFlow, you install TensorFlow GPU, check whether TensorFlow is using GPU, and that's it. By default it should be using GPU. But also Jeff Hitton goes into analysis of how to do this, and that should actually just work out for you. In case you actually have a machine that has GPU, I'd recommend going through his course, and it does cover how to use GPU either on the cloud or on your machine. So yes, that covers how to do that. And now let me just show you how TensorBoard looks. This is now TensorBoard, which is the data of how the graphs are being trained. And smoothing here basically is just smoothing the lines removing the dots, basically where the dots are, how do I put it, basically in your graph line you may have jaggedy lines, so it's trying to remove the jaggediness of between the lines. So that's what smoothing does. I usually don't see the need for it, so I just put it at 0. So this, each in one of these line individually shows how I trained each one of the models. And as you can tell in the pop-up that appears below here, you can tell a number of things about the models thanks to the naming convention. You can tell there's grayscale, edges and colored, with or without dropout. And dropout, as you can tell, doesn't have a higher accuracy, which is smoothed or value, doesn't have a high accuracy level than without dropout. So dropout has a lower accuracy, and that's okay, because the thing is with dropout it actually avoids overfitting. So thanks to that, it will actually perform poorly on the test set but better on the validation set. And that's exactly what you want. You want your data to perform better on data that is not seen, because your data actually never trains on the validation sets. It just uses it as a inkling of how well it's doing. And so another thing you can tell here is the time, well, the date that I trained this on, and here also relatively how long it took to run. The lowest taking about 2 hours 24 minutes, the longest taking 6 hours 33 minutes. And you also have, it has 4 sections, which is accuracy, loss, validation accuracy, and validation loss. As you can tell here, the loss actually went a little bit low, well, a lot lower, actually to about 0 point something, which is, as I said, below 1 is nice. The lower it gets to near 0, the better. You actually never get to 0. You actually want it to be 0 point something or 0.0 something, which is much better. And yeah, so here basically you're just looking at how far the loss has gone. And the key thing with loss, unlike this one, which you actually can tell it's moving consistently downwards, the validation loss without dropout, like you can look if you look at this red line, at some point it's moving down, then it starts moving up. That's the point where it's starting to overfit. It's not understanding the pattern between the validation, so it's trying to look for patterns which it believes are universal, but they are not. But as you can tell, the graphs that actually do move consistently down, like this one's down here, these ones are the ones that actually do use dropout. So thanks to dropout actually killing some of the neurons in between every running instance, they never actually get a chance to overfit. And thanks to that, your model actually still continues to do well enough and get the loss accuracy lower and lower. And actually, because of that, you get higher and higher validation accuracy, because it takes longer to time out on terms of how much patience you put. In which case, my patience is 5 epochs. It gets a high amount of chance to actually get higher levels of accuracy. So as you can tell here, if you compare the dropout without dropout, the one with dropout actually does better in terms of validation accuracy. And that basically now shows you how these graphs work. And just to give you a full understanding of how to use TensorBoard, you can untick whichever sections you have here, so that basically, for example, we have demo here, like it actually didn't do anything. It actually didn't finish an entire epoch, so it doesn't even have a single dot here, but it's been listed. That's the main thing. I didn't actually want to overwrite my information, as I said, so it's there. I can actually maybe look into the folder, delete it if I want to, but I'm actually not going to do that right now. So here I'm just selected only 2 sections. Colored model, basically that's using colored and with and without dropout, and I can tell now how the 2 performed, and I can say maybe using to this using dropout, it took longer, about how many epochs, 26 steps or epochs to finish this. It had an accuracy of about 80%. The validation loss at this somewhere down here started going really high, even though you probably don't want it to go that well, that level of high. Apparently you can actually zoom into this graph, so try and avoid zooming your mouse when you're inside there. So yeah, as you can tell, this graph actually starting point started moving upwards because it didn't have dropout, so it was overfitting. That's a key thing, is try and consider using dropout when you know your model is actually working, whereas if you actually do that while your model actually hasn't finished training or actually done well enough, it's actually just be hampering it actually trying to figure something out. So just to show you the two that we've been using here for edges, more or less they've been working the same, getting the same pattern, even though now without dropout it actually got a little bit higher accuracy, as you can expect with a validation. With the main accuracy validation, basically they were more or less at the same point with the expected of a fitting. And the one model that actually did do the best is GrayScale, because GrayScale allows it to see images in black and white, and because color can be a determinant feature, to put it into context, it should not matter the color of the dog, it should only matter about the features of a dog. So if you give it a black and white image of a dog, it will only look for features, whereas if you give it a colored image, the color may actually be considered as a contributing feature, and it may actually find that dogs which are usually black may actually be misclassified as a black cat if more examples of black cats have been shown instead of black dogs. It's just an example, it doesn't mean that that's actually how it would figure out. But with GrayScale, you have less chance of color actually being used as the main feature that's trying to determine it. So that's the main way to train edges, and now I'll show you how to do that with GrayScale and colored images. And basically we've already finished how to do this, because the only difference is how to feed in the data. So from the top here, everything is the same, how to pass the data. The only difference is in this case this is colored, so the only thing, I actually just don't turn it into GrayScale. So the image comes back with the full color spectrum. I resize it into a 64 by 64 pixel. Same case for this, I don't do GrayScale, so the image comes back as a full color spectrum. And the thing to note is CV2 usually loads image using a different color scheme, which is BGR instead of RGB. The order really doesn't matter, because even if you train your model using BGR instead of RGB, it won't really matter. But the thing is, when you actually want to show your image to someone, if you show it using BGR, it will actually look less realistic than RGB. So provided you always load your model as BGR, it doesn't matter, you don't need to convert it into RGB. I just do it as a best practice method, just in case at any point afterwards you actually want to show how the image looks. Here is the main difference of how you actually feed the model into the data. So when you're reshaping your model, you use 3 instead of 1, which is GrayScale, and when you are putting your convoluted network, you put 3, and then as usual you rename your model so that you know you are working on the colored example. And if you are saving using pickle, specify this is colored, this is the colored pickle data. And GrayScale has the same settings as edges. The only main difference is I don't do the kerning, which was the last thing that I did with the edges. Everything else remains the same. How I fed the data into the model still has the same one dimension as the previous model, 1 dimension, and I'm feeding it to the model, so everything still remains the same. The only key difference is how I name my model and the pickle files when I'm actually saving them. So thank you for watching. That concludes this video on how to design a model using GrayScale. I hope you learned something. Thanks.